Thank you all for coming tonight and for bearing with me through technical difficulties. Even those of us who claim to know about these things kind of break them sometimes, so that doesn't always work. So for my project, I built a solid-state Tesla coil. Ever since I was a kid, I love to make things work. I'm always doing things with my hands. When I was 13, I got into remote control boats and cars, and I would build them from scratch. And so at the beginning of this year, I knew I wanted to build a Tesla coil, but I wasn't sure how I was going to do it. When I found out about the junior project, I immediately was interested. And with help from First Selectwoman Pat Lodra, I got in touch with an engineer who became my first mentor, who was absolutely awesome, Stuart Popovich from a company called Advanced Fusion Systems. He's standing over there not looking and pretending that he doesn't, he's not as good as I am. And about 3 months later, an engineer named John Capoletti joined us, and each of us have put in about 300 hours into this project. So we've worked very hard on this. So in 1627, in his Principia Mathematica, Sir Isaac Newton stated that man would never be able to imitate the powers of a god. In other words, that he would never be able to imitate the forces of nature with something that he had built. In 1891, Nikola Tesla proved him wrong. He built the first Tesla coil. It was exceptional because of its ability to break down and ionize the air around it, basically creating bolts of lightning. He used his coils to do groundbreaking experiments on transmission of electricity without wires, phosphorescence, X-ray generation, and electrical lighting. So let me first explain the basics of a Tesla coil. So imagine a person on a swing. The legs are similar to a resonator circuit. At first, the person is barely moving, and as their legs go back and forth, the swing starts to move. The legs are going to change direction at the peak of each motion, resonating at the same point as the swing is swinging. As each peak of motion is reached, it adds a little bit to the next motion, and the swing arc grows some each cycle. When the arc reaches 180 degrees, the swing is going to begin to slacken, and things will become unpredictable. Likewise, the resonator acts like the legs, adding a little bit of energy to your output terminal each time. And when the voltage becomes too high, things become unpredictable, and an explosive discharge occurs in search of ground. So this cycle, from the resonator circuit to the output circuit, happens in my coil 238,600 times per second. One of the most important things about a Tesla coil is the distinction between electromagnetic and electrostatic waves. Electromagnetic waves are visible light and X-rays or infrared, UV radiation. Those all come in the form of electromagnetic waves, which is the waveform on the top there. However, Tesla claimed that what made his coil exceptional was that it released something new called electrostatic radiation, and that it behaved something like sound waves on the bottom. He proved this by putting his coils through something called a Faraday's cage, the type of which those first type of waves, electromagnetic, couldn't breach. And after Hertz's experiments, this new type of energy became known, the unit for this new type of energy became known as the Hertz, or cycles per second. The importance of this is that in order for a Tesla coil to work, there must be unidirectional electrostatic waves going in every direction. So my Tesla coil. It's not technically a true Tesla coil. It's something called a solid-state Tesla coil. And in making it, I replaced a lot of its major parts with solid-state electronics, things like transistors and all that. And in doing so, I actually made it a much more efficient circuit. The original Tesla coil has something called a spark gap, which releases ozone, UV radiation, and many other things that can kill you. So for that very reason, it became very, very impractical to use in a business. It would destroy any radio equipment nearby, which you can't have in a factory. So by replacing these things with transistors and other solid-state electronics, I've remedied that, and this solid-state Tesla coil can be used in any scenario and is an extremely high-tech form of a high-powered alternating current transformer. So I will power it up here for you. So this, yeah, could you turn the back switch on, off? Dawson, could you turn the back switch off for me?
Do you want these off?
Yes, I do.
Okay.
So this function generator is going to pulse that circuit at a specific frequency, and then you're going to have electrical breakout. Mr. Green, you can Thank you. So that wasn't running at full power actually. I was putting about 95 volts DC into it when I could input probably 120. I might even be able to plug it into a 240 volt outlet. But I didn't want to run into any more technical difficulties like I did before the show and break anything else. So I refrained from turning it up all the way, although it is much cooler. So what you were seeing there was the electrical ionization of the air surrounding the Tesla coil. So the Tesla coil is first producing something called a corona breakout. That's the noise that you hear as I turn up my Tesla coil. What that's doing is it's beginning to ionize the air around it. The electrons are starting to move much more quickly than they usually do, but it's not coming through a focused point yet. Then, once I bring the ground rod close, which is what I was holding, the conductor, which is the coil, is going to reach a certain voltage, and electrical breakdown occurs, which is lightning-like arcs, so you can see, and it will reach out in search of ground. So technically, electrical breakdown is the reduction of resistance in the air around the coil as it exceeds the breakdown voltage. And what that does is it leads to your continuous arc of high voltage electricity. Thank you for watching.
What do you hope to accomplish with your projects?
So I personally believe that Tesla coils are the future of high voltage transformers. A comparable transformer that you would use in a factory, it's just going to be a solid ferrite transformer, is probably going to cost 200 or 300 times what it cost me to build that Tesla coil.
Okay.
And while this Tesla coil technology is new, so a lot of people are unsure about it, it hasn't been implemented in factories much, but once it is solidified within people's minds and they see more of it, it will hopefully replace many of those more expensive parts that you would find. Mr. Holzgruber.
Won't they be loud?
Theoretically, no. So the loudness that you're hearing is the breakdown, and if I were to use that just as a transformer, I would hook up wires to it, and so it would ideally not break down the air around it. That would require further study of what wires you can put on there without exceeding its maximum resistance. So if you put too many wires on there, it'll pull electricity from it faster than it can build it up. But if done correctly, no, it wouldn't make noise, other than perhaps a small noise of the circuit running, but not the noise that you heard. No.
Yeah, so I'd like to think I can answer a technical question, but that's not going to happen. So in a layman's terms, where would we see this in the real world if it were out there?
So before people found out all the limitations of the original spark gap Tesla coil, it was used in radios. I bet the first radio that your parents got all had a Tesla coil in it. It would have been about this big, and then those all got recalled when they figured out that it released ozone into the room. And when you're listening to a radio in a closed room and it's releasing stratospheric ozone, in about 30 minutes you will begin to feel very lightheaded. So after that was recalled, you didn't see it for about 50 years. And then they came up with transistors and other similar micro-sized solid-state electronics that I could use to replace those, like I did here. And now you would find it in an X-ray machine. They can power vacuum tubes. I've seen them power particle accelerators. anything that requires large amounts of voltage to run can run off of a Tesla coil.
So they're taking low voltage and ramping it up?
Yeah, in a way, it's like a step-up transformer. It's taking voltage from a wall and stepping up the amount of voltage you have to something much greater. But a typical step-up transformer operates on a turn ratio law, where the ratio of turns in the secondary coil to the ratio of turns in the primary coil is the same as the ratio of initial voltage to the ratio of output voltage. So my ratio there is about 300 to 1, but my voltage ratio is about 3,000 to 1. So by adding the circuits that I added and by resonating the primary and the second coil to a point, I'm almost making the traditional transformer a lot better. Yes.
Can you talk about what you made that of?
Yeah, I mean, I made it of very basic parts, which is one of the reasons that these are so cool. The entire thing, I mean, the most expensive thing was the garden globe that I put on top. That's by far the most expensive part of the entire thing. I used transistors that cost like 60 cents. Like, the metal box probably was like $3. That's it. There's nothing expensive about it. The copper, the 1,000 feet of copper wire that lines the secondary was $20. The primary was $8 for all that copper. There's nothing expensive about it. If you know what you're doing, then you can make this circuit and you can make a working transformer. That's all there is to it. Yes?
You said that you spent about 300 hours on this project, which is wonderful to hear that you were that focused that long, but what was your biggest failure throughout your process, and what did you learn from that?
The thing about electronics is you like model something on the computer, you follow every single law of physics, you do everything right, and then you make it and it's wrong. And there's never any reason why, but it just doesn't work. And so, I mean, we built probably 10 or 15 different circuits that just did not work. And we built circuits that shouldn't have worked that did work. But a lot of it's trial and error, honestly. You really need to, it's a whole different set of knowledge from knowing how things are supposed to work to knowing how to actually make them work. And I learned a little bit of both of those things with making this.
Would you think, sorry, I'm just gonna follow up. Did your perception of failure, I mean, because you're young, did your perception of failure change because of that? Like, most kids are afraid to fail. They want to do everything right. They hate to be wrong. They hate to fail. Did that change your idea of, hey, failure might be a good thing?
In a way, yes. It was still very frustrating to fail, and it was definitely what motivated me, was that I didn't want it to fail. Like, when I just spent like 40 minutes in there fixing it, I had no idea that I would come out here and it would work. I just replaced the things that I thought were broken, and I was really hoping that was going to fix it, to be completely honest. Because I didn't have the right tools to do it. I didn't have a workspace. So, yeah, that's definitely, but it's motivating. And when you do fail, you learn from it. So, like, if that hadn't worked, I would have learned that. I need to come more prepared next time, or whatever, do more tests beforehand. Yes.
What other organizations or universities are also looking into this technology? You mentioned it's kind of up and coming, but not
when I was doing my research portion of this, I read theses from from Brown students, UNC students, MIT students, all going for master's degree or doctorates in the field of electrical physics. I read things from professors at all of those schools and other schools. It's becoming widely researched, more widely researched, I should say, but it isn't yet being implemented because there are too many unknowns.
From what you know, what you learned on this the Tulsa Coil here, what do you see for the future in the commercial world of using this product, of something that, not that you read about, but something like an idea that you have that it could possibly use as?
I think that this Tesla coil is amazing because what you can do with it is that you can take a small amount of electricity that costs very little. It took very little energy to produce that 120 volts of electricity that I'm pulling from the wall. And I'm creating a 3,000 times that which is amazing because I can use little resources to create little energy, and without anything, basically, with all these simple parts, I can make it into more energy that I can then use.
Well, can you think of,
Really amazing.
knowing that though, can you think of some product that maybe you can develop?
It could power houses. It could, like those transformers that you have on each corner. This is way better than those. It costs, those transformers that you see on each corner, it costs $15,000. This costs 20. And this can produce 5 times more electricity when done correctly. If this was built commercially by professionals with professional parts, not by a kid who's 17, it would be exceptional. But nobody's done that yet.
Why haven't they done that? What's the downside?
There, as far as I can tell, and through all my research, I haven't really found one. What I have found is the reason that it hasn't happened is just because it is recent. The technology that you need to do this didn't come into existence till 2003 to 2005, and even so, even then it was iffy. So like last couple years is really when you've had the very advanced microchips and stuff that you need to make this run at what you want it to run at. So it's still almost in a research phase. People just don't know enough about it to implement it. We're just not far enough along. It hasn't been enough time. But given a few years, I think that we'll begin to see a lot more. Yeah.
If this did become really widespread and everyone used it, how would it get to the homes and businesses? If there was a big one somewhere, how would it get there?
So I mean, it would work in the same way as the current power grid we have. This would be a replacement for a part that we already have. It would be a replacement for ferrite transformers and other air core transformers. It would just be considerably more efficient and considerably cheaper. And the cost savings on the loan would be exceptional. In order to run a power plant off of ferrite transformers, it is many millions of dollars. You replace every single one of those $500,000 ferrite transformers with a, let's even say you make it nice in this one, with a $150 Tesla coil, which is 12 times what this one costs. That would be absolutely exceptional, because just in the cost savings alone, never mind the efficiency, it would save resources and anything else. Yeah, Dawson?
With any of the things that you went in and you said that it by all means should not have worked, but it did, would you ever consider going back and reevaluating what you did and seeing if that would be a greater efficiency and thinking of implementing those sort of approaches to other things?
So a lot of what I did, I followed principles and I did correctly or did incorrectly and it worked, but something that I think I personally need to do is go back and examine those and look at more of the why it's doing these things and not accept the answer of because it's supposed to, because that's what the difference is between most physicists and most engineers and the ones who actually make innovations is the ones who ask why my coil is doing this and not just say it's doing it because Faraday's constant and Ohm's law tells me it's going to, because that's not really a valid answer. One more question? Okay. Yes.
Over this entire process and the many hours that you put in, what was the most rewarding part?
The most rewarding part? Probably when I just made it work for you guys, honestly. I wasn't quite sure that was going to happen, and it was pretty nice when it did. But the other one was the first time that I saw it work. Because we spent 6 months building things and putting things together. We had seen nothing. We had all these jumbles of wires, we had coils, we had machines, but none of it, each individual component worked, but each individual component alone wasn't exceptional. Having a little driver circuit isn't exceptional. There's nothing great about that. So until I got to put it all together and actually see it work, I hadn't really seen anything. So it would have just been a lot of patience, which was hard. But once I actually saw it work, it was totally worth it. Thank you. I also have a gift for my mentor, Stuart, who's here. John sadly couldn't make it. His car broke down on the way home from Pennsylvania. He's still about an hour away. Well, I wish he was here. So Stuart, please come on up.